Start, we start now with Martin Goldstern from Technische Universität Wien, and he will talk on ultrafilters. Ultrafilters without p-point quotients.
Hello, good morning. Let me start by thanking the organizers for organizing this very nice conference and also for inviting me and housing me. I was very happy yesterday to be part of this, to listen to the Matthias Day lectures, and especially happy that I could fill some holes in my bibliography, because there's one theorem which I thought was just some theorem, but it is a theorem of Matthias, that there is an ultrafilter without p-points below it, and I think Mary Ellen Rudin also proved the theorem somehow at the same time. So I always have this discussion with my colleague, that my colleague says, board talks are better, and I say, well, but it helps me to prepare the slides. I like to give slide talks because I can prepare slides. So this talk is an experiment where I prepare the slides, but I'm not showing them to you. You can, if you want, to follow on the slides, but I don't promise to. tinyurl.com/Cambridge 15. Okay, so the slides are there, but I don't promise to follow the slides. Let me just start with some disclaimers. Today, in this talk, all forcings will be proper. All filters will be on omega, and all filters will contain the Frechet filter. So you all know what a p-point is. P-point, it's a and you all know what the Rudin-Kiesler order is, but I will write it anyway. If F is a map from, let's say, from omega to omega, and we have an ultrafilter V on omega and an ultrafilter U on omega, and assume that a set A is in V if and only if F inverse of A is in U. If there exists such a map, then we say that V is Rudin-Kiesler below U. So the minimal ultrafilters, three ultrafilters in this order, are the Ramsey ultrafilters. And I should remark that if U is a p-point and V is below U, then also V is a p-point. Because any partition of V really induces into null sets, induces a partition of U into null sets. And the finite sets that you get from in U will also induce finite sets in V. Okay, you also know that ZFC does not imply the existence of p-points, but continuum hypothesis implies that there exist p-points, and I will just give as a paradigm the construction of a p-point under CH, which is something like undergraduate exercise. So CH implies there exists a p-point, and what you do is the following: you construct a sequence A alpha less than omega 1 of sets which are decreasing. Alpha less than beta implies A alpha is almost a superset of A beta, almost meaning up to finitely many points. And then choose them, let's say, cleverly using CH. It means just do some bookkeeping. And then you get that they all together, the whole tower, will generate an ultrafilter, which also is a p-point. But I would like to see this slightly differently. I want to say A alpha generates a filter on A alpha, namely the Frechet filter on alpha, which I will call, let's say, F of A alpha. This is the Frechet filter on A alpha, And in this way, the F alpha can also be seen as a filter on omega, which concentrates on A alpha. And if beta is bigger than alpha, then the filter A beta will contain the filter A alpha. Okay? And what you're really doing is you have this system of A alphas, which somehow give you a guide. This is a system of parameters. Each parameter generates a filter, and the union of those filters will be the ultrafilter. And the construction that I will do later in this talk will be similar, except that these parameters will be more complicated than just sets. They will be something like trees. Okay, so you know how to get a p-point by this tower construction. Okay, another basic information that most of you will know is the cardinal U is defined as the minimal size of a base for an ultrafilter. Ultrafilter is in 3 ultrafilter on omega. This is U, and it is well known, for example, that Aleph 1 less or equal, let's say B less or equal U less or equal continuum. B is the unbounding number, and other things are known about U. In particular, let me just remind you of a proof that U can be less than continuum. So one proof is the following. You start with CH, fix a p-point, fix a p-point U0, some ultrafilter p-point, and now use a countable support iteration, adding Aleph 2 reals, not destroying U0. What does it mean, not destroying U0? It means that U0 in the extension will still generate an ultrafilter. And this is possible for 2 reasons. One, you can find forcings that add reals but don't destroy a certain p-point. And the other reason is if you iterate such forcings, there's an iteration theorem and that guarantees that even in the limit you will not destroy this p-point. So at the end, you still have U0, which is generated by the U0 from the ground model by Aleph 1 many sets, and you have added Aleph 2 many reals. Okay. There is another consistency proof. It is consistent, there are no p-points, and of course CH must fail in this model. And what you do is you start with CH and kill all p-points, and kill them, let's say, thoroughly, meaning in such a way that they cannot be resurrected to p-points. Now, the aim of this talk, as I planned it some months ago, was to join these 2 models and get the following result: con of U less than C and no p-points. And, well, here you preserve some p-points, here you kill p-points, so you cannot really do these constructions together, obviously. So you have to do something else, and there is a paper which is still in progress of Diego Mejia and myself, and no, I'm alphabetically I'm first, okay, and Saharan Shelach, which I must admit is not done yet. In particular, this last part about the iteration theorem, let's say, I'm sure it's true, but it's not proved yet. Okay, so it is possibly true, yes. But I will give you some ingredients of this paper which I think are interesting for their own sake. In particular, I will tell you what we will use in this construction instead of p-points. It will be, well, like this construction, but more complicated. And I should say this is a large part of my talk, and this part of my talk is based on a paper of Schellach, which has the number 980, and is called Nice Aleph 1 Generated Non-P points. Now this paper, I think at the Heunel birthday conference, when was it? That was...
So that was in 2003.
No.
Yes.
2011? Oh, okay.
But then
Anyway, so a long time ago, I remember... what? He has a birthday every year, yes. Anyway, so a long time ago, I remember Sharon giving a talk on this. The paper is still not published, which has probably various reasons. One of them is that I think it's difficult to read, and we hope that we will revisit this paper in this paper, and then at least 2 people will have carefully read and understood it. No, 3 people, obviously. Well, no, read and understood 2 people, yes. So, okay. So this is the plan. So in some sense, this talk is in 2 parts, and part 2 will be maybe next year. Okay. Now, so part 1 is I will tell you what how to get an ultrafilter which is somewhat Aleph 1 generated, but very unlike a p-point. So I will define what a tree is. So the trees that I use in this construction have a specific form. So first of all trees have the same root, which I call O. Okay. And this root is not a leaf. Not a leaf. So it does have successors. And all non-leaves have Aleph 0 many successors. So in fact, some of the pictures I draw here I could have taken from Natasha's talk, I think. A successor of the root could be a leaf, but in general we will not have that, but it could be a leaf, and then there could be something here, and there could be leaves here, and so on. So this will be a tree. And we also want, okay, the root is O, no, O is not a leaf. All non-leaves have Aleph 0 successors, and all chains are finite. Okay, so it's well founded, and everything stops at a leaf. All chains stop at a leaf. So the chains and the branches and the leaves are in some sense the same thing. This is, and for technical reasons, you should think of these trees as follow. The leaves are natural numbers, elements of omega, and the non-leaves are not elements of omega. But this is, we really work only up to isomorphism, so it's not that important. Let me look at the simplest possible such tree. So it has a root, and the root has infinitely many successors, which are all leaves. Okay, and this tree is really just a subset of omega. It corresponds to a subset of omega. Okay, so it will be, these trees will be generalizations of subsets of omega with some extra structure. So it's not only subsets of omega, this tree also defines a subset of omega, and it defines the Frechet filter on this subset. So I want to make this tree stronger to get a bigger filter. So one way to do it, to choose a subtree of this tree, maybe only this thing. This will be now a subtree, and it will give you a bigger filter. And if I go on like this through Aleph 1 many steps, I'm assuming CH, I will get a p point. Okay, I don't want that. So I will look at a slightly different tree. Let's say a tree with 2 levels. Okay. Now this tree defines, so here I have something I call a front. A front is a subset of the tree which meets every branch exactly once. But for technical reasons, I don't, the singleton root is not a front for me. Okay. The set of all leaves is a front. It's a very nice front. And the set of successors of the root is also a very nice front. Okay. So on this front, I have the Fréchet filter in a natural way. Now on this front, I have a natural filter, which is Natasha. On this front, I have in a natural way Fréchet times Fréchet filter, or Fin times Fin. In the following way, a set is in the filter if I can leave out from this set finitely many of these blocks, and from all other blocks, again, finitely many points. Okay, so I will give a definition. If we have 2 trees, I will call them equivalent. T and T prime are equivalent if and only the following is true. They're both trees, so they have the same root and have all these properties here. And for all s in the intersection of T and T prime, in particular for the root, we have that the successors of s in T are almost the same as the successors of s in T prime. Of course, once you leave one of the, let's say, the tree T and stay in T prime, you have no restrictions on what happens there. But this happens only rarely in some sense. Okay, so let's say W be a front of T. Okay, and then the filter defined by T on the front W is the set of all A in the universe, let's say, but really you're interested in subsets of W. The set of all A such there exists a T prime which is almost equivalent to T and has the property that T prime intersected W. Now, T prime intersected W is a subset of A. So the generalized Fréchet filter defined by tree on its front is obtained as follows. You take the tree, you shrink it a little bit, which means you remove from each successor a finite set, for each node you remove a finite set of successors, and you get a Fréchet smaller tree, and this Fréchet smaller tree will now give you a generator set for the filter. Okay, so this particular tree with 2 levels defines on this front the Fréchet filter, and on this front the Fréchet times Fréchet filter. And now, once you have trees, of course, you can have trees which don't have, k levels, but they have some kind of rank. So you can get complicated trees. I should also define for technical reasons, I will use the notion of an almost front. W is an almost front of T, means there exists a T prime equivalent to T, and W intersected T prime is a front of T. Okay, so in almost front you allow Fréchet many mistakes in some sense. Okay. Now W again doesn't have to be a subset of T prime, but it obviously concentrates on a subset of T, namely on this set. Okay, I have defined what a tree is. I have defined the filter on a tree. In particular, you always get, I will just take f of t is f of t, I will call this max of t. Max of t is a set of leaves, which is obviously front, and the filter defined by tree T is the the filter defined on the leaves of T, which I think of as being in natural numbers. Okay. So maybe I should remark if T1 is equivalent to T2 and T2 equivalent to T3, then T1 is equivalent to T3. Okay, because changing finitely many and then again finitely many still is a change of finitely many. Okay, I've defined the Frechet filter. I've defined the Fubini product of the Frechet filter. Oh, now you know, or you can see perhaps, that this particular filter, Frechet times Frechet, is not a p-point. Well, it's not a point at all because it's not an ultrafilter. It's not a p-filter, by which I mean I have a partition of the set into countably many pieces. Each of these pieces is a null set modulo the filter. Okay, null set because this thing is a large set because you have removed only one successor here. So each of the pieces is a null set, but whenever you take a fuzzy selector set, meaning finitely many pieces from here, finitely many from here, finitely many from here, etc., it is again a null set. Okay, so it is far away from being a p-point. In fact, no filter extending it, no ultrafilter extending it can be a p-point. Okay, so you have in this tree, as soon as you are above the successor of the root level, you have a partition which witnesses the non-p property. Okay, so this tells us how to get ultrafilters which are not p-points. Again, to get an ultrafilter which is not a p-point is an undergraduate exercise, but we want to get some more control on these ultrafilters. So I should maybe write this as a lemma. Assume that T is a tree as above, and W subset T is a front, and assume that this front is not just very close to the root. So W intersected the successors of the root in T is empty. So it is above this successor of the root level. Then the filter FTW is far from a p-point. More specifically, there is a partition of the set W into countably many set which witnesses that no ultrafilter extending this filter will be a p-point, namely the partition given by the successors of 0. Okay. So we will use this lemma later to guarantee that the filter we construct is not a p-point and in fact has no p-points below it. Oh, I also should talk about what does it mean to be below. In this particular example, you have two filters, Frechet times Frechet, and you have Frechet. And you see, because the way I drew it, the Frechet filter is below Frechet times Frechet. But it's not only below geometrically, it's below in the Rudin-Kiesler order. And you see the map here. Okay, this is the map. Okay. In general, if T is a tree and W1 and W2 are fronts in T, and W1 is below W2, that means every point of W1 is below some point of W2, then the filter on W1 is below in the Rudin-Kiesler order the filter in W2. Officially, I defined it only for p-points, but the same definition works for any filter. Okay, and the map is just the obvious map. Every point maps to the point of every point in W2 has exactly one point of W1 below it, and this is the map. Okay, so for fronts, being below means the Rudin-Kiesler order, means below also in the Rudin, implies below in the Rudin-Kiesler order, and later in our construction we will ensure that actually being below in the Rudin-Kiesler order means there is a front which witnesses this. Okay. Okay, now I want to give you a strengthening relation of trees. So for sets it was obvious what strengthening meant. It meant that the set gets smaller except for finally many points. Here we have several versions, several notions of strengthening. So assume that we have trees T2, T1 and T2 are trees. We say that T2 is stronger in the thinning sense than T1 means the following. T2 is a subset of T1, and in fact the successor set of any element, the successors of any S in T2 is a subset of the successors of the same S in T1 for all S in
Martin,
T2.
question. Can I ask a question? You said that tilde is transitive, but is that really true? Because suppose there's some S which is not in T2, but it's in
Yes.
T1 and T3. I mean, the way you wrote it is for all S in the intersection, the successors are.
But it's I can leave it out. I mean,
But that's not T1 and T3.
what?
I don't think the way you define.
Okay, I'm sorry. It's not T1 and T3. I should say there exists. I'm sorry. Okay,
I don't think
that
that's
it seemed to me. Okay, T1 is equivalent to T2 if there exists a T subset of T1, T2 with the property that for all S in
Okay,
T,
sorry.
successors of S in T1 are almost the same as the successors of S in T2. Is that better?
Yes.
I thought this was too complicated. I tried to simplify it, but you shouldn't simplify. Okay. Yes, thank you very much. Okay.
I'm worried about this one. too,
Yes,
because,
please.
suppose I have T1, T2, and T3, and I have this subtree of T1 and T2.
And a subtree of T2 and T3, and you intersect both of them.
And they are empty.
But suppose the intersection doesn't have enough branching. Suppose the
No, it has, because the branching is almost the same as in T2.
The root is
no, that needs to be added.
Success of S in T.
Now I'm happier.
Okay, thank you. We are all happy. Thank you. Okay. Yes. Okay. Okay. Thank you. I'm so happy that there are two people listening. And who knows who is listening, on the web. I will check my emails later. Okay, so one way of thinning the tree is just to thin out the successors to some obviously infinite set still, okay? And of course you want to have splitting points stay splitting points, okay? So this is a subset, and if this is non-empty, then also this should be non-empty. Okay, leaves stay leaves, but non-leaves have to stay non-leaves. Okay, so this is one way of shrinking a tree, and this helps you getting closer to an ultrafilter because you can decide whether you want to be in or out some set. Okay, and so maybe I should say, fact, if T is a tree and F is a function from the leaves of T into 2, then there exists a T prime which is thinner than T, and F restricted to the leaves of T prime is constant. Okay. By doing essentially downward induction on the tree. So this shows that if I take a tower, an omega 1 length tower of thinner and thinner trees, I can get to an ultrafilter. Okay. Of course, I might have always trees of height 1, and then this ultrafilter will be a p point. So in order to get a non-p point, I have to make sure that there are levels between the leaves and the root, okay? And to make sure that the fronts of these trees, on these fronts of these trees, which will be Rudin-Kiesler quotients, I don't have a p-point. I have to add a front below every front, okay? So this is, I need another notion. So T2 is finer than T1 if the following is true. T1 will be a superset of T2. No, sorry. The new set T2 will be a superset of T1. So I will add new nodes, but I will not add new new leaves. I will just add new nodes somewhere in the middle, okay? And find the maximum, okay. So example, I have a tree like this, which I call the Fréchet tree, okay? Because it induces somehow the Fréchet filter. And I add new nodes here, and these nodes will be, this will be connected to infinitely many, this will be connected to infinitely many, and I get the Fréchet square tree from that. And I have now ensured that the filter that appears on this level will not be a p-point. But now here I have a quotient which threatens to be a p-point, so I have to add another level, okay, below it. But I have one many steps to do that, so I can do that, okay. So, and okay, so this is the finer relation, and then there's another relation. T2 is Fréchet below T1 means just T2 is equivalent to T1. Okay, so this can go both ways, but for notational purposes, I write it like this. And the relation T2 and the relation less or equal between trees is just a transitive closure of these three. Fine, thin, and Fréchet, of the union of those. Okay, you can think of which order you do it, and really the order is irrelevant. Okay. Okay. So, oh, time is flying. Okay, so I will just claim, without proving, which I didn't intend to do anyway. So, let me say theorem. Assuming CH, there is a sequence of trees T alpha less than omega 1, which is decreasing, such that various things hold. One of the things that should hold is that the union of all the f T alpha, this will be an increasing union, because the stronger the trees get, the bigger the filters get, is an ultrafilter on omega. And to get to an ultrafilter, I will use this fact in successor steps, to decide all the possible sets. Okay, but I can get more. It's an ultrafilter. 2 for every front W in any T alpha, there exists a beta bigger than alpha, such that W intersected the successors of 0 in T beta is empty. So whenever I have a front, at some later stage, I have added another front below it, okay? And therefore, the ultrafilter, the union of all f of T alpha on the front, on this particular front intersected with T alpha, this will be an ultrafilter on W, but not a p-point. So all the ultrafilters that I get from fronts that appear somewhere will be non-p points, okay? And then I will also get Okay. I will also get for the following about these fronts. Whenever I have two fronts that appear in some tree, they may be like this, okay? But because of my fact here, I can thin out the tree to see only one half. So the two fronts will be one above the other. So if W1 is a front in some T alpha 1 and W2 is a front in some T alpha 2, then there exists a beta bigger than alpha 1, alpha 2, such that W1 intersected T beta 1. Formally, this will not be a front, but it will be an almost front. And W2 intersected T beta will be comparable. Comparable, I mean they're either the same or almost the same, or one is everywhere above the other, which means that the corresponding ultrafilters are either the same or one is Rudin-Kiesler above the other. So the ultrafilters that I get from fronts will be linearly ordered. So what is still missing is I want all Rudin-Kiesler quotients to be of this form. So I will need another fact. Maybe I'll call it a lemma. Okay. Assume T is a tree and F is a function from the leaves of T into omega. So not into finite set, but into some infinite set. Now, in general, this function might be one-to-one, okay? In which case, one-to-one is wonderful. You know, then this function will induce an isomorphic ultrafilter. The function might be constant. Okay, this is also wonderful because then the image will be not a free ultrafilter. So okay, then there is a tree T prime which is thinner than T, and a front W of T prime. So I start out with some T. I have this function here which has some values. I will find a smaller tree, T prime, and a front W in T prime, such that for all S in W, the function f restricted to T prime above S and the leaves of that. So for every S, if I look at the function only at these values, this function will be constant. Will be constant with some value Cs. And the function S maps to Cs will be one-to-one. Now what does this mean? This means this function induces a Rudin-Kiesler image of the filter I have here. But if I look at the stronger tree and at this set, the filter induced on this set is isomorphic to this Rudin-Kiesler image, because this function S maps to Cs is exactly the Rudin-Kiesler isomorphism. Okay, so from this lemma I can get here 0.4. 0.4 doesn't fit here. So I will write it here. This is 0.4 from the sequence of ultrafilters that I get for all V which are Rudin-Kiesler below the f of, I will give a name to this. The sequence will be called T vector, and this ultrafilter will be called f of T vector. Okay, the union of all these filters. So whenever I have a Rudin-Kiesler filter below T, below this filter, there exists an alpha, and there exists a front in T alpha so that V is isomorphic to the union of all the T beta bigger than alpha. I take the filter on T beta on the front W intersected T beta. Okay, so every filter which is Rudin-Kiesler below the filter I constructed will be of the form that it appears on some front below the leaves, and therefore it will be a very concrete Rudin-Kiesler image, and therefore it will be in this linearly ordered set of ultrafilters. Okay, so I will get a filter which is in some sense Aleph 1 generated. Of course, not really, because these filters here, they're not generated by one set. And this filter is in some sense far away from a p-point. On the other hand, it hopefully inherits enough elements of the p-point property. So partition. Okay. So now I will tell you how to kill p-points. Okay, which is what Lawrence indicated yesterday. So I will just show you the forcing. So let D be a p-point. Then there is a forcing SP of D killing D thoroughly and preserving our ultrafilter F of T, the ultrafilter we constructed. Okay, and in fact, well, okay, I should say there are some. I can get something more from this ultrafilter, which I will need later. I will need the property that this will be a Q point, also, and a little and more. Okay, I need slightly more than a Q point. Okay, Q point means whenever you partition omega into finite sets, you can find a selector set in the ultrafilter. But I need this not only for finite sets, but also for specific specific infinite sets. In particular, for those infinite sets which appear here. For these partitions, I will also need selectors. Well, no. This is not true. I will just say Q point and more. Okay. Preserving D, in fact, preserving all ultrafilters which are not below D, and our ultrafilter is not a p-point, therefore it's certainly not below D, which satisfy, well, 5, okay, meaning Q point and more, being essentially like a Ramsey ultrafilter, except it's not a p-point. Okay. So this forcing kills D thoroughly, so we just need to iterate this forcing all the way through all the possible p-points, and then we have killed all the p-points. What is missing, as I announced at the beginning, is the iteration theorem for this doesn't quite work. So we know that a single step cannot kill our ultrafilter, but we don't have a proof that the omega step doesn't kill it. Okay, so next year I will talk about that. Okay, again, I will not prove anything, but I will show you the construction, the definition of the forcing, okay, of the forcing D. And this, I should say, this is older than, I think this appears in Schellach's proper, already in the proper forcing book. So we look at the following. First, I will tell you what the generic object will be. The generic object for the forcing, so SPD, the generic object will be a sequence eta 0, eta 1, etc., where each eta I is in 2 to the I. A sequence 0 ones of length I. Okay, this will be the generic object. There will be no relation in particular. They will not extend each other. Okay, there will just be a sequence of sequences. Okay, a condition will approximate this. So a condition will be a condition P will be a tree where at level K the elements will be sequences E0 up to EK minus 1. The elements of level K, at level K we will have such elements, and each EI will be in 2 to the I. Okay, so at level K we will have somehow an approximation to the generic object. Okay, and below it at level K minus 1 is just a shorter sequence. Okay, so the elements are sequences of sequences. This sometimes gives some rise to some confusion. Okay, but not all trees are like that. Okay, so we have to do the following. Let's say that L is bigger than that L is bigger than K. Yes. So we will say that a node S at level L is K splitting, means the following. I look at S, so S is something like it's at level L, okay. S is this thing. I look at the successors of S. So the successors of S are sequences which have one more object, okay. So I will just ignore the S in them. So this is a subset of the set of all E. It's a subset of 2 to the L. Okay, the successors are those things that can be attached to S and still staying in the tree. Now I look at the set of all E in the successors of S, and I restrict them to K. Okay, so these are things of length L, which is quite big, and I only look at the K initial segment, and I want that everything appears. Okay, so K splitting means that the successors, they are of length 2 to the L, but every initial segment appears. If you want, you can say every initial segment appears exactly once. That would result in a dense set. So this is K splitting, and the set of all these, and okay. For a condition I will require that for all K, the set of all L such that all S in level L of P are K splitting. So I look at all those, for each K I look at those levels where we have K splitting, and I want this to be a large set. Okay, so I want to have trees which are quite bushy in some sense with respect to the ultrafilter D. Okay, so this forcing has some nice properties. It has some kind of fusion which we can prove using the p-point game. So this works only for p-points. Using p-point we can show fusion, we can show properness, we can show omega-omega bounding, and we can show a property called the PP property, which is a weakening of the Sachs property. I will tell you how to show that that the D will not be a p-point anymore. So in the generic extension, we get this family eta 0, eta 1, eta 2, eta 3, etc. Okay. Now we read infinitely many reals of this family. We will read xi will be a real. Xi in place n will be eta n in place I. Okay, so here I have some I, and I look at the bits. Here we have bits 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, etc. So the xi will be read off horizontally from these etas. Okay. Now we don't know what happens here. Let's say we put zeros here. Okay. So this is true if for n bigger than I, and for n less or equal than I, it will be 0. Okay. Let's say it doesn't matter very much. So xi of n. So xi of n corresponds to a set xi of a subset of omega. This is the characteristic function of some set. And these sets will witness that these cannot be extended to the p-point in the following way. For any subsets of omega, I define xd as x if x is in D, and omega minus x is not in D. Okay. And we will show, I will not show what I'm claiming, we will show in the paper that SPD forces for all ultrafilters D prime extending D, the xi's will be a witness to the non-p property. For every D prime extending D, the family xi D prime, I in omega, these are countably many sets which are all in the ultrafilter, because if xi was not in the ultrafilter, I switched it around, has no pseudo intersection in D prime. Okay, so this means that the D cannot be extended to a p point, and moreover, if I do SP of D and then continue with my iteration, and this iteration is nice, it should be proper, it should be omega omega bounding, and it should have this magic PP property, then still the same is true. Okay, so even after omega too many steps, it cannot be a p-point. Now properness is preserved, omega 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 bounding is preserved. There is something called the weak. There are several. There's a spectrum of different PP properties, and one of them is preserved and good enough for this theorem. So this is killing the p-points is no problem. Preserving our ultrafilter is still open, and well, next week I will visit Saharan again, and we will try. We'll have one easy proof which is completely wrong, and we have a more complicated proof which may be wrong, and we have to still fix that. So at the next conference, I hope to present you that. Thank you.
Any comments or questions?
Yes.
In your model, it seems that the continuum is just omega 2.
Yes.
Is there any
I
chance?
have no idea. I have no idea, because coin rails will destroy all ultrafilters. So, of course, you can do some try to do some product, but I don't know. Would be nice, of course. Everything with large continuum is nice.
Well,
Yes.
and you haven't used the word creature. in your code.
That's true. These trees are infinitary creatures, if you want. Okay, so they're monsters. Okay.
Monsters.
Yes. Yes.
Yeah.
Okay.
How is the EK related with this EI two lines above? I mean, you said the level is sequences of sequences, and how
Well, I mean,
how do you
the successors of S is a subset of S times 2 to the L. Yes, and I just, well,
Oh yes.
Okay. so I just ignore this. Okay. And the ethers are, well, of course, obviously I didn't say that, but the ethers are just those E's that survive the forcing. Okay, there will be a generic branch to this tree, and this will be the ethers. Yes.
So is the PP particularly necessary for this construction? Because all these original proves that like there are no P points or there is one selected. I think you can get away with those PP properties.
anyway, it's true. I mean, our forcing has the PP property and the iteration has it. But of course, doing different proof might be interesting also. But the original proof doesn't use this SP of D, I think. There's something called PF omega, which... Oh, no, I'm sorry. You mean the proof that there's exactly one
Yeah, like for
Ramsey
example,
ultrafilter?
I think that one works without mentioning PP property, I don't know.
Okay, I will look at that. Thank you.
Well, if there are no more questions for Martin, let's thank him once more and we'll adjourn until 11:30.
Thank you.